summarize the recap, let me just remind you of a few things. First, during the afternoon coffee break, we'll have a second picture of the conference with the speakers of the second week. Then after that coffee break, we have the poster session, so remember to put up the posters. We're thinking very hard to come up with a new, shiny, useless prize for the best poster. And third, we have the dinner today. I think you all got the details, so we are all invited. We hope to see you there. And now we leave you with the third lecture by Dio.
Okay, let me just give you some references. Okay. So first things first, there was a question that I couldn't recollect the answer to yesterday, which was what happens when you have the tensor product of complementary series. And it's, at least for SO2, this has been worked out. And the answer depends in detail on whether, what values the parameter lambda that ranges from 0 to 1 takes. But it'll include, it may or may not include complementary series depending on this parameter. It's just a side remark. So, yeah, so where are we? Okay, so we motivated the problem. Broadly speaking, of course, the need for a quantum theory for expanding spacetimes, and we discussed some classical features and dynamical features in the regime where the evolution is dominated by the most relevant term in the effective action, which is the cosmological term, lambda. And we discussed a large host of cosmological type behaviors, classical behaviors, which could include solutions that bounce, classically, or have a Big Bang type behavior where there's a classical singularity in the far past. Yeah. And we also discussed the causal structure of the pure de Sitter solution and emphasized the fact that there's cosmological horizons, yeah, that are reminiscent of those of black holes, but not quite the same because of effects like the one of Gauss-Wald that allow us to access the complete Cauchy surface before reaching the future infinity. Okay? Now, the plan, yeah, so what I'd like to do today is continue discussing from this more group theoretic perspective some aspects of quantum fields in a fixed de Sitter. It complements a little bit what we saw in the previous lecture, in that I'll try to be a little more general about the properties of these quantum fields and not focus on a particular type of field. And after that, I'd like to discuss some properties of a special state in the quantum field theoretic Hilbert space. And then I think it's good time to move back to gravity. Okay? So that's the plan. Are there any questions before I start? What? These are examples of recent work that I think are exemplifying the kind of topics I'm mentioning. This is 2306, 0, 0, 090, and this is 2403, 16166. Yeah. Okay. So if you remember, the basic idea or the basic object that we were exploring last time was the idea that if I have a complete Cauchy surface, yeah, in this universe, so let me remind you of the global coordinate system. So here my Hilbert space will live on a spatial slice, which is a 3-sphere, okay? I can append to this surface a field-theoretic Hilbert space of states, which can be decomposed into the class of unitary irreducible representations of the relevant isometry group. For instance, in 4 dimensions, this is SO4, 1. In 2 dimensions, this was SO2, 1. And we discussed some of the properties of this set of irreps, yeah. And what I'd like to do today, is elaborate a little more. So we had it was a more group theoretic discussion last time. I'd like to elaborate a little more on the connection to the field operator, yeah, and these particular irreps, okay? So what were the irreps? And I'll continue with the simplest instance of this group, which is SO2, 1. And if you remember, we had these sort of 3 different categories. We had this all infinite dimensional unitary irreducible representations, but they had sort of 3 different flavors. There was the principal series, where this lambda parameter was equal to 1/2 plus I nu. We had these complementary series, where lambda took values between 0 and 1. And we had the discrete series, which had an additional index, which is a sign having to do with whether it's of the type of a highest weight or lowest weight, yeah, where lambda took a positive integer value, okay? And remember that the quadratic Casimir had an eigenvalue that was given by lambda times 1 minus lambda, okay? Now, this is a statement that is purely group theoretic. It's the result of the classification of these UIRs. However, we would like a field theoretic perspective of this. And in the spirit of the way we associate properties of quantum fields or the single particle Hilbert space of quantum fields with unitary irreducible representations of the Poincare group, we could imagine here a similar association, okay? And the particular association that we'll mention is that different types of fields, yeah, effectively very heavy fields, so massive quantum fields in de Sitter, or the single particle Hilbert space of massive in units of the de Sitter length scale, quantum fields in de Sitter space furnish the principal series. Light quantum fields in units of de Sitter furnish the complementary series. And gauge, what in 4 dimensions is effectively the set of gauge fields or massless fields, have a furnish these discrete series or exceptional series representations, okay? So the classification from the mathematics literature on these irreps ties nicely to the type of particles that we have. And I should emphasize again that whether the particles carry half-integer spin or integer spin is important in that some of these representations are not present, for instance, the complementary series, in the case of half-integer spin, okay? So all of these subtleties are important, and I should perhaps add to that a slightly more philosophical note that having as complete an understanding as possible of the particle content or the field content allowed in a de Sitter universe is important if we are to start building simplified toy models that we can solve exactly. Yeah? Because they may involve particles that are not simply scalar fields. They may involve a more elaborate spectrum of particles. As an example, if we are looking for a solvable quantum field theoretic model in de Sitter, we might be interested in studying something like the Schwinger model in a de Sitter background. That's an example. I won't have time to discuss it, but it's basically quantum electrodynamics in two space-time dimensions on a fixed de Sitter background that involve charged fermions interacting with a U1 gauge field. And that's an example of a model that we can study and solve on a de Sitter background, and it involves fermions. Yeah? So this is a typical thing that if we start scanning, if we're seeking theories that have good structure or elaborate enough structures that they can be solved beyond the tree level or even one loop, we may have to resort to a broader class of representations. Yeah? So this is why this approach might yield. Now, how do these properties manifest themselves? So let me make some comments about the late-time structure of quantum fields. And I'll start with just free fields for now, just to give you a flavor of what the late-time structure of field operators look like. And so the question is the following. Imagine I have some free field, yeah, as a function, so some free field operator. Okay. I'll call it phi, but you can imagine this to be some general field. It could be not necessarily a scalar. We can ask the question of what is its behavior, and here I'm going to resort, because I'm interested in local patch, I'll resort to the coordinate system of the planar patch, yeah, just for the sake of clarity. So what kind of properties does this field operator, or free field operator, exhibit at late times? And so the characteristic behavior that one sees is that in the limit where eta goes to 0, the operator acquires a rather universal behavior at the free level. Yeah, so you get essentially two terms, two operators rather, yeah, in your late time expansion. So you have eta going to 0. When eta when lambda, yeah, so this is lambda over here, remember, so let's work in SO2, 1 again. So when lambda is in the principal series, you have the following behavior. You have a term that goes like eta to the lambda, yeah, which means that it dilutes. So eta goes to 0. You have a plus 1/2, it dilutes. And you have an eta to the 1 minus lambda that also dilutes, yeah? So you have a situation where you have a field that dilutes, and in the original coordinate, so if you remember, there was another time coordinate that we could study this with respect to. The behavior goes like e to the minus t. Okay, so this is sort of a dilution, rather e to the minus t over 2, yeah? So you have a field that decays as a function of time. This is a massive field that as a function of time decays as the space expands. This makes sense. It's a massive field in an expanding spatial volume. And you have two operators alpha and beta, yeah, that each transform nicely under conformal transformation. Sorry, this delta should be a lambda and a 1 minus lambda. So you have two conformal operators appearing, yeah, at late times. So you've partitioned your field phi hat into two operators that transform nicely under the action of the SO2, 1, yeah. And they furnish, but they transform with different, what you would call conformal weights. So one transforms with weight lambda, the other transforms with what's called the shadow weight sometimes, 1 minus lambda. Yeah? Now this is an important point to emphasize. So if you're more familiar with the story in ADS, where you typically associate a single conformal operator with the near boundary expansion of the field. This isn't the case over here, because the boundary, or what you might imagine as the boundary, is a late time surface, yeah? And so the field, phi hat, much like a quantum field has to be built out of A and A dagger, the field phi hat has to be built out of two non-trivial operators. And in fact, these operators generally don't commute. Yeah? So this is in the principal series now. Oops. Okay? So the structure we have at late times reveals a few things. First of all, the action of the isometry group at late times becomes a conformal action, yeah? It acts like a conformal group on the late time surface. Secondly, with respect to this conformal behavior at late times, you discover two distinct operators associated to the quantum field operator phi hat, yeah? Phi hat, I'm assuming to be a Hermitian operator, yeah? Okay, so for that to be the case, alpha and beta are related by Hermitian conjugation. In particular, that means that these are complex operators. They're not Hermitian operators, yeah? So A dagger is equal to B. And in addition to that, they have a non-trivial operator algebra, yeah? All of these things are qualitatively different from the behavior that you might see in the context of ADS, where you have a single operator and you don't have this commutation relations, yeah? So this is important to emphasize. And you can think of these operators as a type of late time creation and annihilation type operator, except for the fact that the natural vacuum at late times is not annihilated by either of them. We'll return to that point. Okay? Now, in addition to this is another curious fact, but important fact, which is that whatever state you're in, yeah? So whatever state you're in, let me just call it psi, inside of our field theoretic Hilbert space, if I act with one of these operators on this state, yeah? So imagine I try to create a new state by acting with one of these operators, okay? And I compute the norm of this state, the new state. So imagine I start with a normalizable state. It's in the Hilbert space, therefore it's a normalizable state. Okay? So now let me act with this state with a conformal operator. Yeah? And let's compute the norm of this state over here. Okay? So then we have to conjugate this thing. Okay? We'll obtain the following. Yeah? Generally speaking, this norm over here, yeah? Or if you want to make life a little bit simpler, we can act with a Hermitian operator. Yeah. So generally speaking, the norm of this new state is problematic because we have to compute the overlap of operators at a coincident point. Yeah? And so it'll generally not be finite. So this is to be contrasted with ideas about state operator correspondence, where in CFD we often act with a local operator and create a state from the point of view of state operator correspondence. Any analog of that, when people try to make analogies between the conformal structure at late times and the action of conformal operators, is bound to run into trouble. Yeah? So there's no notion of a state operator correspondence in terms of the conformal structure one identifies at late times in the de Sitter spacetime. Okay? So what I'm trying to do is give you a flavor of how things are different from expressions you may have seen in the context of ADS in order to understand the physical properties a little bit better. Yeah? So I hope that point is clear. Now, what happens for the complementary series? Just the contrast with the principal series behavior. So in the complementary series, the late time structure changes slightly because now you have remember, now lambda is real valued, yeah, and you have the following late time structure. You again have a decomposition into two conformal operators, alpha and beta. However, since lambda is real valued, yeah, if I take the Hermitian conjugation of my operator, phi is a Hermitian operator, lambda being real implies that the reality properties of these operators is different than that of the principal series. Yeah? Now they're Hermitian, okay? And so the decomposition of the field is in terms of Hermitian conformal primary operators in the complementary case, as opposed to complex operators in the principal series. Okay? And so the character of the operator, of the conformal operator structure, is sensitive to the particular unitary reducible representation. Again, a more refined version of the type of structure we may be familiar in Euclidean CFD or ADS CFD. Yeah? And here, again, the operators have non-trivial commutation relation. But now, instead of an I, rather, maybe I got it wrong over here. Yeah, sorry. There's a 1 over here. Instead of a 1, there's an I. Okay? So this is a nice exercise to go through in detail. But the basic point to make is that there's a much richer set of conformal operators at late times in any ideas that people may have regarding associating conformal structures with a late time surface. One has to account for this much broader set of structures. Yeah? Now, similarly, if we have a quantum state that obeys the symmetries of de Sitter, and then we'll discuss that in a moment. Yeah. So imagine we have a state that happens to be invariant under the de Sitter isometries. In other words, it's a state annihilated by the generators of the de Sitter symmetries. So these conformal operators will have a nice property. Yeah, for instance, assuming they don't annihilate the de Sitter invariant state, which is a reasonable assumption as it happens, will have a nice property that they'll have so the standard conformal correlation functions, yeah? So this is one of the nice attributes of the de Sitter symmetries, looking like conformal symmetries at late times. Again, this is a statement about the operators themselves. The operators are defined at late times in the following way. One can extract them from the field operator. But one thing to note, which ties to a question that people had about unitarity bounds in the previous lecture, is that let's take the complementary series as an example. So there, remember, lambda can range between 0 and 1. And in particular, that means that this over here, yeah, so this is the correlation, piece of the correlation function of the quantum field at late times, yeah. If lambda approaches 0, yeah, which is unitarity allowed, yeah, the rate of decay of this correlation function becomes quite slow, yeah, almost constant in the strict limit, okay? And so if you recall in the first lecture I mentioned that cluster decomposition isn't quite as powerful in de Sitter, and the reason is that one can have enhanced correlations in the infrared where fields don't decay, even massive fields don't decay exponentially at large spatial separation, and they can even decay very weakly polynomially, yeah? And so, quite ironically, even though the character of the spacetime is one of an exponential expansion where you might naively assume that everything is diluting, quantum correlations can remain rather enhanced. And that's an important feature, an important quantum mechanical feature. It has a classical counterpart in the behavior of waves that allows you to have an imprint of fluctuations of light fields in a universe that's expanding at a remarkably rapid rate, yeah? This isn't a particularly intuitive thing, but it is true nonetheless. Okay, good. So the point really that I wanted to make in this sort of like patching up the group theoretic results with properties of the field operator algebra is that if one tries to envision a structure that has to do with the conformal structure of the de Sitter isometries at late times, one will have to confront a structure that is involving a series of non-trivial operators, conformal operators, yeah? Just to give you sort of a caricature of what it might look like, that have a non-trivial operator algebra among themselves. These are not, unlike what happens in a Euclidean field theory, completely commuting structures. These are non-commuting, yeah? And moreover, the action of these operators doesn't create normalizable states. And so it's quite a subtle structure. You'll have to, and moreover, you'll have to deal with contact terms, Yeah, so notice that these kind of commutation relations imply that the expectation value of things like alpha with beta may have contact terms in them. Yeah, and you can't forget about the contact terms, because the contact terms, these delta functions over here, are intimately tied to the quantum mechanical nature of the field theory itself. I should say the origin of this contact term over here is precisely related to the Heisenberg algebra that the field operator and its conjugate momentum obey, okay? And that's just the quantum mechanical nature of the quantum field theory. And so, all this to say is that there's a rather elaborate conformal operator algebra that we have to take into account, including contact terms, including all possible reality conditions and hermiticity conditions, in order to start envisioning what a conformal structure might look like. And that's tied to questions that people are interested in regarding the association of conformal field theories with these type of spacetimes. Okay. Good. Are there any questions about this? Hopefully this was a little less abstract than the representation theory, but this is the structure at late times. Okay. Do I want to say anything else about this? Yeah.
Can you say some words about the entanglement structure of the vacuum state due to this high correlation of large correlations?
Yeah, so that's a good question. The first order business will be to see how to even compute entanglement, but and that is really a question that would require me to discuss the properties of the quantum state itself in more detail. So let me, well, okay, to avoid entering a tangent that I'm not sure where it will take me, I'm going to suppress myself. But I will, yeah, because I'm going to talk about the sort of cleanest version of the question of entanglement entropy in de Sitter, which is the entanglement between fields across two of these cosmological horizons. I'm going to discuss this in quite some detail, and I feel that's the cleanest version of this question. So let me suppress a quick answer for a long answer later on. Yeah. Yeah. What I can tell you for sure is that the character of the entanglement will depend on these type of features, the representations and how they contribute and whether or not they're gauge fields. These have important imprints in the entanglement structure. Okay. Now, I wanted to, so very quickly before going to gravity, I wanted to make a few more comments about the quantum state itself, yeah? So, at the level of the quantum field theory, there's no particular state that is distinguished in terms of what we would call the vacuum or the lowest energy state, because there's no time translation invariance. And in fact, there's an infinitely large field theoretic Hilbert space, and there's many states that we could consider. However, once again, there is a natural question we can ask, which is whether there exists in this Hilbert space any state that obeys the de Sitter invariance. In other words, a state that's annihilated by the generators of the de Sitter group. Now, if there is no such state, yeah, we could entertain the possibility that there is no such normalizable state in the Hilbert space. that would indicate that somehow quantum effects have disrupted the symmetries, or that there's something like a spontaneous symmetry breaking of the de Sitter symmetries. Yeah? So we could also entertain the possibility that there are multiple such states. Okay? I know of no general result that indicates that this should be unique, which is a little different from the Poincaré story. But here, I'm going to assume that such a state exists, at least one. And then one would like to understand its properties, okay? In order to be able to contrast it to the case of gravity. And part of this was alluded to in the previous lecture. So one way to characterize the state is from this operator point of view. You can characterize the state by studying all the correlation functions of operators that it produces. But there's also a Schrödinger picture for the quantum state. And in this Schrödinger picture, one imagines representing the state as an overlap, yeah? So it'll be generally a function of time. We can call it eta to comply with the notation of the previous lecture. And there can be a profile phi, where this profile over here is an eigenstate, yeah, of, well, the field operator phi, yeah. So let me make that clear. Imagine that there's some state over here that when I act on it at a constant time with a, well, at some given eta, yeah, that I get phi of x. Okay, so that's an eigenstate. Imagine there's such a state. Psi over here, yeah, will be an overlap, okay, of this state with the abstract quantum state psi. Okay, that's the idea. And so the Schrödinger picture of quantum field theory is just a way to represent a quantum state in a field operator eigenbasis. Okay, that's all. It's like psi of x is equal to psi overlap x. And the features of this de Sitter invariant state will manifest themselves in the following way. So all I want to tell you to conclude a little bit the treatment that we have of the quantum field theory is what are the structure of this object over here. Yeah. So this object can be studied with a variety of methods. It can be studied using path integral methods, perturbatively at least, not just semi-classically, but to lead at the loop expansion as well. But generally speaking, in the late time limit, so actually it'll be a little simpler to talk about the logarithm of this object. This object will have a structure that takes the following form. And here I'm going to assume a perturbative expansion, so a weak field expansion. So, yeah, and well, let me take the absolute value for the moment. So you have a series of non-local terms okay, coding the correlation functions. And yeah, sorry, I'm going to 4 dimensions because it doesn't cost much to write this down. But it'll generally have the following type of structure. So it will be a polynomial expansion in this variable phi of x. And these objects over here are formally, I've written them as if they were expectation values, but this state over here is not a state in the field theoretic Hilbert space. Yeah? But they do take precisely the form and obey precisely the ward identities of a Euclidean conformal field theory. So the manifestation of the de Sitter isometries in the late time structure of the wave function is that you can open up the wave function, at least for in the weak field expansion, and this isn't a this is a general statement under the assumption of the existence of a de Sitter invariant state, yeah, in a series of endpoint functions that obey the conformal ward identities, yeah? So the reflection of the de Sitter symmetries in the late time Schrodinger picture is that you can accommodate the features of the wave function into this series of correlation functions, but the general rules of these correlation functions will not be those of a standard Euclidean conformal field theory in regards to the reality conditions that it satisfies, yeah? But this will be the structure of the state. So what? Yeah. So this is at late times, and maybe I should emphasize this geometric property more carefully. So let me emphasize this more clearly. It's a good question. So it has to do with the following geometric feature. So let me write down in this coordinate system, let me write down the isometries of the de Sitter group. Well, let's write down a few that are fairly straightforward, yeah? So we have the Euclidean transformations of X, yeah? And the translations. We have the dilations of, let me use a different variable, kappa and X, where kappa is a positive number, yeah? But we also have a more non-trivial set of transformations where eta goes to, let me see if, let me not try to write it down off the top of my head because I'll make a mistake. Here. I'm almost sure that I've written it down. Oh yeah, perfect. Where eta maps to the following. And X maps to the following. Okay. So this over here, yeah, So this over here is the set of isometries in the planar patch for DS4. Yeah, we can count them. We have 6 over here because we have 3 different spatial translations. We have 3 different rotations. We have 1 dilation, that gives 7. Yeah, and we have this parameter B, which has 3 values as well, so that gives 10. Yeah, so these are the 10 isometries. And the observation I wanted to make, which I hope will help with all of this late-time conformal structure, is that if we project these onto the surface eta equal to 0, yeah, which is the late-time surface, what do these become? Well, these become precisely the set of conformal killing vectors that map the flat metric on R3 to itself up to an overall conformal factor. Okay? And so the action of the de Sitter isometries, which generally maps a point in the manifold to some other point, when pushed to the late times, manifests itself as the conformal group on R3. As such, many of the late time structures of the quantum field theory acquire a conformal covariance under the conformal group in R3. And so it's natural at sufficiently late times to expect that the quantum objects, provided that the de Sitter symmetry has not been broken or spontaneously broken, transform in a nice way under the conformal group. Of course, if you were to ask me whether the 2-point function of a quantum field, so let me contrast this with the statement of a 2-point function of a quantum field for 2 arbitrary points in de Sitter. Yeah. So again, imagine we have 2 different points, and in terms of the embedding coordinates, let me call these x and y, where x and y are points on 5D Minkowski, subject to the condition, well, the condition that we wrote down. So that they're points on the de Sitter hyperbola, yeah? So now you could ask me, well, what about, say, the 2-point function of a field for 2 arbitrary points on de Sitter? And if it's de Sitter invariant, what you can say at best are not that many things, yeah? You can say that it'll be a function of the de Sitter invariant product, the Lorentz invariant product of these 2 points in embedding space, yeah? So that'll give you a very specific functional dependence that will depend on all 4 space-time coordinates, yeah? You can, in the coincident point limit, yeah, require that it has, a particular power, so that's the standard coincident point singularity of a 2-point function, the Hadamard behavior, so that you can request. And finally, based on this Charlin-Lehmann representation, you can decompose this into the free 2-point functions, yeah, of the theory. But to give you a flavor of what those look like, yeah, as opposed to the simple conformally covariant expressions over there, the free 2-point function, for instance, sorry, I've been calling it lambda, so will look something like this. Lambda bar is the shadow of lambda. It looks something like this, yeah? So it'll be a hypergeometric function. This will be a number that depends on the space-time dimension. I think it's 2 for DS4. And then you'll have 1 plus x dot y over 2. And here there's some factors of pi. This one I don't know if I've written down. Let me see if I wrote this one down. yeah. Anyways, it's some factors of pi, but the space-time dependence is what I wrote over here. Yeah. For pi squared gamma 2, whatever, 1. Yeah, but you see, it's a much more elaborate structure. Yeah, so this Green's function over here, this is the Whiteman function, depends, of course, on the representation. It's invariant under lambda goes to lambda bar, and is de Sitter invariant. It turns out the properties of the hypergeometric function are such that this has the standard singularity properties and branch cut properties across the light cone. But it's not something as simple as 1 over x minus y to the 2 delta. Although, when you take these points all the way to the future boundary, of course, it yields precisely these kind of conformal structures. Yeah? And so it's important to distinguish the simplicity of the late time behavior and the language of conformal field theory that becomes very manifest with the more general set of correlation functions and their analytic structure in the whole manifold itself. Yeah? And I think that's an important point. We often are motivated to study things at late times, but the real objects of the quantum field theory that code the full structure will likely be more reminiscent of this object over here. Yeah, and it's important to study those objects as well. Okay, so I think that's what I want to say about quantum fields. Yeah. Yeah. Where's the?
So here your discussion, you're looking at the late times, but would it be similar if you looked instead at early times?
Good, good, indeed. So the argument I gave over there, I could have done essentially a time reversal version of the argument and reconstructed it over here. And in fact, tied to that question is a very interesting question of imagine that I wanted to understand the class of correlation functions that had points, some points over here and some points over there. And those set of correlation functions will also have simplified structure. Yeah.
Hi there.
Yeah.
This is not the same thing as if I was imposing antipodal points in the bulk
so I'm assuming here only the standard coincident point singularities, and I'm not assuming states that have non-local singularities.
Okay.
Yeah. Had I done so, one might encounter additional de Sitter invariant states, which are known as alpha vacua, and people may wish to study those as well, although their status at the interacting level is a little more subtle. So here I'm assuming standard Hadamard behavior. Yeah.
Okay.
Okay. Good. Now, so that's what I wanted to say, I think, about quantum field theory in de Sitter. It's an elaborate structure. It's very rich in a sense. Yeah.
Sorry, just a small question. This free 2 points function is for a particular representation, or because
so this is for a spinless representation labeled by lambda. So lambda here would be something like, well, the Casimir would be lambda in 4 dimensions times 3 minus lambda. Yeah.
Okay, because my question was going to be if we have problem here in the discrete series because the lambda.
No, sorry. This is for, so this is for a generic representation. Good.
Okay.
So this is for a generic representation.
Okay.
Yeah.
Thank you.
Excellent. There's an indeed adding to the subtlety and aiding to the conclusion. Already for the generic representations, we have to deal with these elaborate structures, and it only gets more interesting if we start including gauge fields and things of the like. Yeah, and so I think the take-home message here is that this quantum field theory, even in a fixed de Sitter background, is an open problem. we're slowly scratching the surface of it. And I think an important challenge, as people start to explore this, is to identify examples of exactly solvable, non-trivial quantum field theories in de Sitter that can guide us with the more general statements, yeah? And in that light, I think it's worth emphasizing a very sort of simple version of that, which is this two-dimensional quantum electrodynamics in de Sitter, which is a theory that has an all-loop expansion that we can study and explore these kind of features, okay? But I won't discuss the details of that here. But I encourage you to read the paper. Now, okay. So that's some of the general flavor of quantum field theory. We took it from an operator point of view. We took it from a Schrödinger point of view. And we considered it from a group theoretical point of view. All add value to the discussion, yeah? And what I'd like to do now is go back to gravity, yeah? And see what happens to all of these structures when we add gravity to the story, yeah? Because after all, the problem that we started with, that we motivated, was cosmology, and there is no cosmology without gravity. And so it's important, I think, to incorporate the effects of gravity into the story. And the reason I ended with the Schrödinger picture is that I would like an expression. I would like to think about whether or not this hypothesis of a Hilbert space, or this postulate of a field theory Hilbert space, carries forward to gravity. And if so, what are the rules of the gravitational Hilbert space? And that's, well, a very elementary question in what the theory might look like. Now, how does one proceed with this question? Yeah? So I think one of the approaches that has been prominently studied has been the canonical approach, yeah? And so I'd like to make some comments of what that entails, okay? So in the canonical approach, so let me see. Oh, yeah. Yeah? So what we do is we decompose, yeah? So this is sometimes called the ADM picture, yeah? Arno Desser Missner. So the idea is to decompose the class of space-times in Lorentzian signature in the following decomposition, yeah? Okay, so we decompose our metrics. This is a 3+1 type foliation of space-time. Yeah, and we have what's called a lapse function. Yeah. Ah, so Guy covered part of this? Okay, so. But okay, but it. Yeah. So, okay, in that case, let me remind you of this canonical approach. So this over here, it's not bad to hear it twice. So this over here is the lapse function, which is a function of the spatial coordinates and time. This over here is an induced metric on a spatial slice, which is a constant t slice. And this over here is a shift, known as a shift vector, which tells us sort of how one foliation and another are tied to each other. Okay? And the important point to emphasize is that being a gauge theory and having these 4 diffeomorphisms, gravity is a theory that has constraints. Yeah? And so how is that manifested in the theory? Well, it's manifested in the fact that the conjugate momenta of n and ni vanish, and instead n and ni impose certain conditions on the phase space. Yeah? Now, one important thing to note, yeah, it's a caveat I'll mention here that eventually may come back to haunt us, is that this function over here, n, is positive. It's positive values. It would be redundant for n to live across the whole real line. And so this object over here is actually valued on R+. I'll leave that comment for the time being, but it's a comment that's important to bear in mind. The reason for that, for mentioning that, is that often we try to treat these quantities as Lagrange multipliers, but when we use a Lagrange multiplier, really we're assuming that the field lives on the whole real line to implement a delta function in the integral. Anyhow, that's a side remark. Yeah, so I'm just making a simple comment that the following integral is a delta function, yeah, only when I integrate x across the whole real line. If x is integrated across the positive part, this is no longer the case. And so when we talk about variables that we want to interpret as Lagrange multipliers, but they don't live on the whole real axis, the constraints that are following from them may not be the ones that we think they are. But with that caveat aside, thank you for the clarificational question, we can write down the constraints, the gravitational constraint equations, that follow from these 4 quantities, yeah, maybe they were written previously, and I'd like to write them in terms of the canonical momenta of the metric field. So here we view the induced metric, much like we did in the late time expansion, as one of our coordinates in phase space, and there's a canonical conjugate to this, which is nicely written in terms of, so here I have kappa, which is related to the square root of the Newton constant, root h, and kij is the extrinsic curvature. Okay. Okay, so k, if you will, is defined in terms of the shift and lapse as follows. Dot is a time derivative. Yeah. So this is the standard Lie derivative with respect to unit normal along this Cauchy slice. And that's our conjugate momentum, and our constraint equations, just to remind you, if you saw them previously, well, anyways, you can never see them enough. So. They take the following form. So there's something called the Hamiltonian constraint. Where we have 1/2 kappa root g, and we have an object with 4 indices, g, I, j, k, l, which acts essentially like a metric in the space of metrics. I don't know if that terminology was used. 0. And so here I should say I'm also assuming pure gravity. If you have matter fields, you can incorporate them into this equation. And what it would add is the energy of the matter fields, okay? And if you have a more general effective field theory with higher derivative terms, they will also contribute to this equation, okay? So that's the Hamiltonian constraint, which comes from varying n. And then there's a momentum constraint, yeah, which is significantly simpler, which is just that pi ij has a vanishing covariant derivative. Okay, now what is the meaning of these equations? This one over here is fairly straightforward. It says that physics should be invariant under diffeomorphisms that are tangential to the Cauchy surface and map spatial points along sigma to spatial points along sigma. Yeah? It has to do with a constraint associated to the spatial diffeomorphisms. This one over here is an equation saying that the physics should be invariant under your choice of how the splice, provided its space-like, is embedded inside of your 3+1 spacetime. Yeah? And for the sake of simplicity, it may be useful to consider the case where sigma is compact. The reason for that is that I would prefer not to have any potential boundary terms of leakage of flux in my treatment, yeah? So these are the equations, and I'd like to contrast these equations with the kind of constraint equations that appear in ordinary gauge theories. In ordinary gauge theories, the constraint equations are typically always linear in the conjugate momenta. If you write down the constraint equations for Yang-Mills theory in terms of the phase-space variables, you'll note that they're always linear in the momenta. The gravitational constraint equations already stand out in that regard, in that the Hamiltonian constraint is a quadratic functional of the momenta. Yeah? That's an important point to note. Okay? What it codes is the statement that the total energy, or the total energy density along your Cauchy surface vanishes. We saw a version of that in the FRW equations, if you remember. Yeah? And you might wonder here, and it's an important question to wonder about, is how can it be if you have matter obeying the null energy condition or some other standard positivity condition, and you have excitations of the gravitational field, stars, black holes. How can it be that the gravitational theory has to have vanishing energy? This seems like a severe restriction in the configuration space of your theory. However, it's important to note that this object over here is not, so if you view it as a metric on the space of metrics, yeah, sort of a target space metric, if you will, is not a positive definite quantity. Okay? So, if you will, imagine you had a quantum mechanics on some curved space, and the Hamiltonian was the Laplacian on this curved space, yeah, and we had something like a Schrödinger equation. We typically assume this Laplacian is a positive definite quantity. Yeah? So the analog here would be that this object is the Laplacian, except that the Laplacian isn't positive definite. It has directions which are negative, so it's more like a Klein-Gordon operator with a negative direction at every spatial point. Yeah? So that's a second very important distinction, that precisely the reason, but that means that I can have negative kinetic energy, which if you remember, the A dot over A squared that I wrote in the FRW, if I wrote it with the other terms having positive energy, was a negative A dot over A squared. plus energy. But that means that gravity can support negative kinetic energy, yeah? Even if the configuration has very small curvature, the spatial slice, so R is the Ricci scalar of the spatial slice. Even if lambda is vanishing, but you had some positive energy, you can accommodate for that positive energy configuration with negative gravitational kinetic energy. This is a remarkable feat that gravity exhibits. And so for those of you who are curious, actually I have here, maybe it was also written down, but let me write it for you again. You can never write it enough times. This has an explicit expression. Yeah? And what in the space of all metrics are these negative directions, yeah? So again, we're viewing this as a metric where one of the indices of the metric is this ij, the other index is this kl, so this is a huge metric, yeah? The directions that are not positive definite, it's a nice homework exercise, are related to directions in the space of all three metrics. Yeah? So this is Hij is a general, remember, general spatial three metric living on sigma. Yeah? The directions that are carrying this negative kinetic energy are precisely the directions that are associated to the overall volume of Hij, or the overall scale of Hij. So a fun exercise for you is if you take Hij and write it, so do the following simplification as some function, a, maybe even a of t of x, and compute this creature, you will see quite directly there that such configurations in the space of all three metrics carry negative kinetic energy, yeah? And so, interestingly enough, the negative directions have to do with things like the overall scale of your three-dimensional space, yeah? And this was already noted in the paper of Bryce DeWitt, which you should also read, very important, in the 50s. So he wrote 3 papers on canonical quantization of gravity, and it's remarkable how many things he already notes in that paper. Yeah? Now, okay, so what I'm trying to emphasize is that the physical content of these equations, well, this one is fairly standard, but the physical content of this equation is quite remarkable. Yeah? And it shows clearly that although there are these very stringent sounding constraints in gravity, like everything has zero energy, in no way does that restrict the original classical configuration space of your matter fields. Yeah? Okay? So, okay, so those are the canonical equations, the constraint equations. And what is proposed, so the proposition of DeWitt, Wheeler and DeWitt, which is one of the ideas that people have tried to pursue in this business, is that we should take this equation, this classical equation, seriously also at the semi-classical quantum level, okay? In other words, that this equation should be understood to be an equation governing the quantum mechanical features of the metric in the regime of low curvatures. Yeah. Yeah.
So you said that the negative values are associated to with the metric.
Are associated to the overall scale, yeah.
I see. In this sense, if we consider like only vacuum solutions with a vanishing Ricci tensor, then this metric would be restricted to positive values, or it's not like that?
you cannot restrict. So this is an equation over the whole configuration space.
No, I agree, but
Yeah.
for instance,
There will
metric
be
that you-
configurations where this is positive, and there will be configurations where this is negative.
No, I agree, but for instance, the metric that you suggested,
Yeah.
there's
So
a restriction, and that it has a vanishing vowel tensor. If I
Yeah.
suppose it's something that had the opposite, like yes, that it was pure vowel tensor and with vanishing Ricci, then
Yeah.
it would be positive definite, or it's not
there is a
associated?
subspace of three metrics which will allow positive definite G. Yeah.
Okay, and
But it will be an arbitrary restriction in the space of
yes,
all
I
possible
agree,
three
I
metrics.
agree. Just correct.
Yeah.
Thank you.
Thank you. So, indeed, but it's important, and this can be quantified, and it's important to understand what subspace of three metrics has these eigenvalues in superspace, in the space of all three metrics. So now I want to discuss the Wheeler-DeWitt hypothesis. And the spirit of the hypothesis is that although we don't have access to the fully quantized theory of a gravitational field, perhaps we do have access to some of the quantum features of the gravitational field at low curvature for short enough timescales and small variations of the field itself. This is not unreasonable. For instance, we're comfortable with the idea that we can consider the quantum scattering of gravitons in asymptotically Minkowski space, yeah, including loops. So these are not ideas that are unfamiliar. The proposition here was to discuss the quantum features of the metric in a more general setting, which isn't asymptotically flat, but rather for something like a closed universe, yeah? So that was the idea. So, and the idea was that, well, perhaps in the spirit of this Schrödinger picture, there exists a Hilbert space. So now it's some gravitational Hilbert space, yeah, which is built out of the following larger Hilbert space, which is given by the set of all functionals of the three metric itself. Yeah? So imagine that there exists such a space. Okay. I haven't specified for you what the inner product of this space is, and that's a subtle question. But imagine that there exists a space given by the set of all functionals of the three metric Hij. Yeah? So this is some large functional space. And now, let's ask the question, let's propose that the set of gravitational, semi-classical or canonical states are those for which psi is annihilated by these constraints. Yeah? So that's the proposal. Okay? And any state, okay, so in the functional basis, I should say that we would represent pi ij as I times the variational derivative of Hij, okay? So then this becomes a functional differential equation, okay? Very complicated one. And in fact, you can already complain here that when I go from the classical to the quantum picture, you're going to have to identify ambiguities in the operator ordering of these operators, and that's true. So there are operator ordering ambiguities, because a given classical theory can be the classical limit of a large class of quantum theories. That's just how it goes. And but that there exists some quantum completion, that these, in other words, the assumption is that these equations are the classical limit of some quantum completion, and that in that regime, in that limit, yeah, the Hilbert space of gravitational states is given by wave functionals that satisfy these equations. Okay? So that's the hypothesis of Wheeler and DeWitt. And of course, I can't really call this a Hilbert space quite yet, because I haven't specified to you what the inner product is. And herein lies some of the trouble, that the inner product that you might imagine to be the one that's most natural to the problem is a little analogous to the inner product of trying to quantize a particle subject to the Klein-Gordon wave equation. Yeah, so going back to this analogy with the Laplacian, imagine that you had a quantum mechanics where your wave function, yeah, was subject to a Laplacian with indefinite signature. So that's an example of an operator that has one negative eigenvalue and one positive eigenvalue. So the time translation, or maybe if it's a quantum problem, we can add time dependence as well. Yeah. So the inner product that's time translation invariant, sometimes called the Klein-Gordon inner product, yeah, is not one that has good positivity properties. So the price to pay when you have the wrong sign in your kinetic term, yeah, so that's another nice exercise, is that if you try to build an inner product for this kind of theory, you will have to make further restrictions on your space of states in order for the inner product to be positive definite, yeah? And so, although we were happy about the fact that there was a negative eigenvalue here classically to accommodate for the constraint and a large classical configuration space, it's interesting that in the most naive attempt to quantize this theory, we run into trouble at a very basic level, which is how to define an inner product. Okay? And so that's something to comment on. I'll return to that in a moment, but at least what Wheeler-DeWitt offer us is a new set of equations to try to solve. Yeah? So that's good. So that's progress, new equation. Now, generally speaking, this equation is rather hard to solve. I would encourage you all to try, but don't spend 10 years trying to solve it. Maybe 10 weeks. It's a hard equation to solve, as you can imagine. It's a functional partial differential equation that involves functionals of the 3 metric and so forth. Now, this equation is not so hard to solve, because this equation simply states that psi, so let's solve the easy one first, that as a function of the 3 metric, yeah, psi is a spatially diffeomorphism invariant functional of the metric, yeah? So whatever this functional is, it should be a diff-invariant functional of Hij, yeah? So an example of a diff-invariant functional of Hij that's very simple is it's just the integral of the square root of the determinant of Hij. Of course, this is a much more elaborate function because a priori this need not be a local functional of Hij. In other words, it doesn't have to be a functional that's a pointwise integral of the field at one point. It could be a non-local functional of Hij. Yeah? That's an important point. Much like it was for the scalar field when I wrote down the wave function. If you remember, I had integral dx phi, integral dx, dy, phi x, some 2-point object gxy, phi y. Similarly here, this will be a non-local function of 3 metric, okay? And that's important because you expect the quantum field theory to code non-local correlations, okay? Secondly, and this is more subtle, Yeah. So that's good. We have at least taken care of one piece of the puzzle. We have this object over here. Now here again, there is one regime, maybe it was discussed, but let me re-emphasize it, where things simplify, which is the large volume of Hij regime. And why would we anticipate that things simplify in that regime? Remember the universality of lambda, that in the deep infrared, a large volume, it takes over everything. So we can expect that at least the portion of psi in the regime where in the deep infrared is governed very sensitively by lambda. And that you can imagine, because if you have an induced metric, Hij, with a very large volume, yeah, how does the Ricci scalar scale for this volume? The Ricci scalar will scale like 1 over the characteristic length squared. So that'll be driven, Ricci scalar is local, large volume, driven to 0. So it's subdominant. This term in the equation is subdominant compared to this term over here. Yeah? Yeah. 5 minutes. Damn it. Okay. Okay. So, in fact, in the large volume limit, the equation is driven to a significantly simpler equation that I'll simply state. Yeah. So if we take the regime, say we have a parameter a tilde squared Hij, and we take the limit where a tilde goes to infinity, yeah, one can show that the equation satisfied by psi in this regime, or rather the absolute value of psi, so one can show a series of things. One can solve the problem in a series expansion of a tilde. And, well, let me write it more specifically. Psi will have the following type of structure. The leading contribution to psi will be a phase, yeah? And for this, because I only have 5 minutes, let me write it like this, which to leading order will depend, well, let me retain the IQs, will depend on the volume. It'll be a phase, a local functional of H, which oscillates parametrically fast with respect to the volume. The second term will go linearly in A dagger, in A tilde, and it'll be essentially given by another phase times another local functional of H times R, where R is the Ricci scalar of H, yeah, and I'm removing this factor of A, yeah, so it has a very highly oscillatory behavior to leading order, and it's a pure phase, okay? This is characteristic of the WKB approximation of a wave function. So this large volume limit is characteristic of a WKB approximation. And then the next term is not a phase, it's the absolute value of psi. And this object over here, yeah, has the property that it has to be, in addition to a diff invariant functional of H, it also has to be invariant under local Weil transformations of Hij itself. In other words, the constraints to leading order in this large volume infrared regime of this very complicated equation simplify to the condition that psi is a wave functional, and this is, I haven't selected a solution yet. This is true for all possible solutions to the wave function. Is a wave functional with a rapidly oscillating phase that is locally built out of the metric field H, plus an absolute value, which is not a phase, but it is a Weil invariant functional, Weil cross diff, yeah, Weil cross diff invariant functional of the wave function as a function of the metric itself, yeah? Now, you may worry that this type of constraint is too restrictive. Maybe there's no such function. However, just to quench that concern rather quickly, at least mathematically, such Weierstrass diff invariant functionals certainly exist. And to give you a very simple example, you can compute the functional determinant of the conformal Laplacian. So I think it's something like this. So this functional over here, just to give you an example of a Weierstrass diff invariant functional of Hij, the functional determinant of the conformal Laplacian of a three-metric Hij is, with rigorous grounds, a Weierstrass diff invariant functional, non-local functional of Hij. And so at least as proof of principle, this restricted set of Wheeler-DeWitt equations admits solutions, yeah, and it's natural to hope, and perturbatively one can also explore, that it'll admit more, okay? So interestingly enough, in the case where lambda is positive, just to conclude, our equation has an attractor point in the large volume limit that admits a much more structured solution space where we might be able to actually anticipate some more of the features of this wave function. Okay, so that's, compared to the general complexity of the Wheeler-DeWitt equation, quite a remarkable thing. So what's left then is, well, we have two challenges left. One is, what is the inner product, yeah, of these wave functions? And B, is there any particularly distinguished solution in the space of all Weierstrass diff invariant functionals that we may so wish to study? Yeah? Okay, so I guess we can run out of time now, so we can ask some questions. But this is where we're at. Yeah.
Okay, questions? Come on, don't be shy. You have time. Maybe Pedro wants to give you time.
All right.
So I want to connect this WKB expression that we found here. At least my intuition from WKB is that usually you have that when the spectrum becomes like continuous, and here we are in the late time limit, but at the same time, before you told the idea is to match that in the late time the equations we want to solve where we have like the quantum equations, but here we have like a continuous spectra. So that's two ideas. I don't know if they are related, or maybe I'm crossover everything.
Yeah, let's try one more time.
Yeah, why we have like a WKB here asymptotic expressions.
Yeah.
That for me, WKB, we usually have it when we have like continuous spectra. So we expect now that
Well, so already here I would say, well, first of all, the operators that we're dealing with are, infinite operators with a priori continuous spectra, but also you should remember that here we're dealing with a quantum problem where h psi equals 0. So you have to tell me the spectrum of what for this problem? Yeah, so I think
I would say H,
but H is only has one eigenvalue, 0.
Okay.
And so I think the question, you may want to try to think of how to formulate the question in such a way that it's tying to these equations, yeah.
Okay.
But certainly the operators themselves, H hat is like X hat. These are operators that a priori don't have discrete spectra.
Okay. Okay. Maybe confuse me the WKB expression.
Yeah. So the only thing I was pointing out here is that this is an analogy to the highly oscillatory nature of the WKB wave functions.
Okay.
Yeah.
Okay. Thank you.
Anyone else?
Since you asked that, since you said that the module, the last part of the wave equation, the wave function should be Weyl invariant. Does
Yeah.
that mean in 2 dimensions every metric is the state for every?
Yeah. So things simplifies even more in 3 dimensions. Yeah. So if you imagine you have DS3, so then it's true you have a 2 metric. Yeah. And if it's furthermore Weyl invariant, the best hope you can have is that the metric has sufficiently complicated topology so that it depends on the modular parameters and the complex structure of the homogeneous surface. Yeah, because if not, there's not much that it can depend on in this regime. That might indicate that there's significantly fewer solutions, at least on a topological 2-sphere in the 3D case. But in the 4D case, the point I was making is that there's a large, even if you restrict the Cauchy surface of a 3-sphere topology, there's a large class of potential solutions. Yeah.
Maybe also related to that, one question. Before, when you were talking about the correlation, the late-time correlation functions,
Yeah.
you also had the special conformal ones.
Yeah.
Do they somehow show up here?
Well, here, yeah, so I didn't have time to emphasize this, but remember that here, the Sitter isometries are part of the diffeomorphism group itself, and therefore they're subject to the constraints of the diffeomorphism group. And so there's a sense in which all states have to be annihilated by the generators of the de Sitter isometries themselves. Now, that isn't to say that everything is featureless. Of course, if there's a classical solution, which is pure de Sitter, there may be a wave function that peaks sharply near that classical configuration, and the fluctuations will be still governed by the isometries. However, observables will themselves have to satisfy the analogous constraints. And so it's a little more subtle to sort of see or physically characterize the nature of the de Sitter group. This will return to, though, from a different point of view, which will be a Euclidean point of view, where they will reveal themselves in a completely diffeomorphism invariant quantity rather nicely. Yeah.
Okay, there are no further questions. We thank you again.
Thank you.